can be of two types. One is the one which we use in industry, like weather forecasting is there, and then in finance, and then the ones in academia. So we are actually more interested in what is happening in the academia, and we'll be dealing in detail of how to convert the problem in your work domain to a predictive modeling technique. Okay, so that's the objective of this FDP. We will introduce the core concepts and techniques which are used to launch predictive analysis. We'll go through the theory as well as the tools, as I've said in the inaugural also. We'll be looking at some practical examples. So we, at the end, on the last day, we have two use cases. So one will be on networks, which I'll be delivering, and one will be on distributed systems. So basically, my area is not on this predictive modeling, but I use these tools in my research domain. So what I'm going to do is I will give an idea of how to use these tools in your research domain. Your research domain may be anything, but how can you use this in your industry, in your research domain? And then we also look at some industry perspective. And the industry perspective, as Manoj will be giving more details on the industry perspective. So the outline of the talk is as follows. I'll start with preparing the data for predictive modeling. So we call this as exploratory data analysis, or in short, we also call it as EDA. Okay. And you may also have heard some other words here, like some people call it like pre-processing. Then there are other names for this: data munching, wrangling, and all those. But all of them more or less mean the same thing: preparing the data for predictive modeling. Okay. Then, so after we do prepare the data for predictive modeling, and this first tab is common for everyone. So in the next tab, we have this. So in the next step, we have this model selection techniques. Model selection techniques will help you out. In the model selection techniques, we'll be looking at how to predict a continuous. If you have a continuous or binary variable, then which modeling technique you should use. If you have time series, then which modeling technique you should use. And these two techniques, decision tree and neural networks, this is common for. And this is more or less kind of a generic kind of framework, which is for both continuous as well as binary variable. So the motivation behind this FDP or workshop. So first thing is, as I've said, predictive modeling is used in a number of industry cases, like, for example, sales forecast. Okay. And then in banks also people use it. So if you want to, my voice is low, it seems.
Hello, sir.
Yeah, is it better now?
Sir, the sound is well. Sir, can you please go to the previous slide once again?
Okay. Yes.
Sir, what is ETA, sir, actually?
EDA stands for Exploratory Data Analysis. EDA.
And sir, ETS. Sir,
I'll come to this in detail. I'll come to this in detail in a little while. And then I have got a few slides on this. What is
Sir, what is the full form, sir, of ETS, sir? ETS?
EDA is Exploratory Data Analysis.
ARIMA and ETS, the time series analysis.
Yeah. I'll come to this. I'll come to all.
Okay. Okay, sir.
I'll come to all of this one by one. Okay. Thank you. So, so the motivation, as I was saying, so motivation can be of two types. One is for industry and the other one is for academia. So industry, so you all know we use it for weather forecasting, and then for in case of banking. Okay. In banks also, suppose you want to give a loan. I'm a manager of a bank. I want to give a loan. Okay. So I want to give the loan because I want to earn interest, but at the same time, I I need to ensure that I don't run into too much of risk. So when I give a risk, I want to find out whether the person to which I'm giving the loan, whether he'll default on the loan or not. So those kind of predictions also we can make with this kind of tools. But the one which we are, so means it helps us in taking calculated risk. Calculated risk. So that's what I've written out here. But what we are more interested out here is in the domains in which we can use this kind of tools. So the domains which I've identified out here, these are only a few domains. One is social networks. Social networks is very common nowadays. Everyone is using social networks, and there's a lot of work going on in social networks. So that's one domain which we are, which is of interest. Then computer networks, this is my area, computer networks, network security. So I'll not delve into much of this because I'll be talking about this on the last day. Okay. And then we also have how to use such kind of tools in distributed systems. So here in this case, Professor Partho will be talking about. So let me just talk about this link social networks because here this we will not be dealing in detail in the next 5 days. So social networks, there are a number of places where you can apply this. Okay. So one is like I said, link prediction. Link prediction can again be of, if I look at link prediction, again be of two types. Link prediction can be again of two types. One is you say static. Okay. Static means the link between the nodes, the edges between the nodes, they do not change. And the other one is dynamic. Dynamic means the edges keep on changing. Okay. And in link, when you say in static, so links do not change, then what do you want to predict? So basically what we want to predict here is what will be the relation between, what is the relation between two nodes? Okay, what is the relation between two nodes? Even if the link, if there's no change in the link. So to give you an example of this, I was working on a project for network security. So wherein we are looking at a terror network. We are looking at a terror network, and in those terror network, there are some nodes which are not very active. Okay, but they are the main nodes. They are the main nodes, and there are some nodes which are active, but they are not the main nodes. So means the mastermind may be someone who is not very active. So based on the kind of post that he makes, based on his comments, okay, we have to try to find out that particular node is linked with which other node, although there may be no physical link between them. So that's what we try to predict here. This is what we try to predict here in case of static. In case of dynamic, we want to find out how the network will grow. So if there's a node between a few friends, so how this collaboration will grow in future. So that's about dynamic prediction. Then when we talk about community formation, it's an extension of link prediction. It's extension of link prediction. Here we want to find out what will be the frequency and volume of interaction between the nodes. Recommender system, I have got a slide on recommender system. This is very important. This is also a very important area of research. Okay. And then the risk prediction and planning and intervention. So these are the areas in social networks which you can work on. So I'm just pointing out the areas where you can do further research if you are interested in social networks. So talking about recommender system, so a very good example of recommender system is Netflix. Netflix is huge success is contributed to predictive marketing. And they started using this kind of tools way back in 2000, 20 years back, right? And what was their idea? Their idea was to predict what users would prefer, which movies users would prefer to watch. Okay? And their prediction goal was very modest, 10%. Even with such a low prediction accuracy, they could build millions in terms of money, okay, in terms of resources. So what we did was basically analyze the customer behavior and buying pattern and build a recommender system and then recommend the movies to the customer. And there's a research paper on this also. If you go to and search on the web, you'll find that there's a research paper which was published in 2016 based on this, based on their model. Okay, and you can see how popular the research paper is. There's more than 1100 plus citations. So that's the kind of work that you can do with predictive modeling. So I'm just trying to motivate you. So let's start with some basics. So what is predictive modeling? As the name implies, predict the future events, okay, based on historical data. And what is our main goal? The main goal here is we have an unknown function f, suppose. We have an unknown function f, and then our main goal is to build a model for this unknown function. So this unknown function f, in some places, it is called as hypothesis. In some case, they call it as a decision function, a decision model. And these are my predictors. We call it as predictors, or we also call it as independent variables. So these are my predictors. Means I will be using these variables. I'll be using these variables to predict the future event. And this is my so this is predictors, or these are also called as independent variables. So those who work on this area will know these are known as independent variables, and this is the dependent variable. This is what I'm trying to predict. This is my dependent variable. And how do I build this model? Build this model using my past data, historical data. So these are my training samples. So I've indexed them with I. So here it means to say that there are m training samples. There are m training samples. That's what I want to say. That I equal to 1 to m means there are m training samples. And this index at the top means this is indexing the ith row. This indexing I means ith row. So I equal to 1 means I'm looking at the ith row. Y I equal to, I'm looking at the ith row. Okay. So y is the dependent variable that we are interested in predicting, and x is the independent variable which helps to predict the dependent. Now, if we look at predictive modeling, so I call it the 3 sides which are possible on data. One is hindsight. Hindsight means you look backward to know what is happening. You look backward. So this is not data analytics, but you just look backward to say what is happening. Insight. Insight is actually what is, this is data analytics. So we try to find out what is happening. We try to understand what is happening. Okay, this is my data analytics. So like, for example, if I'm looking at sales record, so in the first quarter, what is the sales volume? In the second quarter, what is the sales volume? In the third quarter, what is the sales volume? So that is data analytics or insight. But we are looking at a trend, but we are not doing any prediction out here. And then when we look at this past knowledge and try to predict, then this is foresight. So that is analytics. We look forward. So these are the 3 possible, three sides which are possible in data. Hindsight, you look backward to know what is happening. Insight, you look into the data to know what is happening. And foresight means you try to predict the future, looking back, using the past knowledge. So if you have any doubts, you can also interrupt me here. So what are the tools which we use for prediction? Okay. So one is Sas Statistical Analysis. This is from SAS Institute. It's used for advanced business prediction, crime investigation, and this is a commercial software. And then we also have SPSS, Statistical Package for Social Sciences. So this is also a very old package, and this is also a very popular one. So it has a vast library of machine learning algorithms. It is a vast library of machine learning algorithms. And this is also a commercial software. So these are all commercial softwares. But what we are basically interested out here is this R. Okay, this is an open source software used for statistical computing. And this is very much in development. Right at the moment, there are about 18K packages and it's growing. Okay. The other tool that which you can use is Matlab, but Matlab is a commercial software. So in this particular FDP, we'll be mainly working on R because it's open source and it works on all the platforms. And then if you are a beginner, and then I strongly recommend that you can use this tool, Weka. You can search on the web, Weka. This the main advantage of this is it is GUI based. It's GUI based. Okay, so what you do is you upload your data and then you select which algorithm, machine learning algorithm you want to execute on that particular data. Press click, then that's done. Okay. So it has a collection of machine learning algorithms, DB scan and all those stuff, all the machine learning algorithms, most of the machine learning algorithms, and it is GUI based, so it's very easy to use. So if you are a beginner, then I recommend that you use this Weka. Okay. And then once you are more familiar with machine learning algorithms, then you can graduate to R. And if you already have hands-on experience on machine learning, then you can start with R, or maybe some of you have already started with R. So why R? So R is a statistical computing, and it has a large library set, as I said. It's easy to visualize data and display outputs using this. And since it's open source, there's no black box mysteries. Everything is open source. You can see all the code. And then it runs on all the three commercial operating systems, Windows, Linux, and Mac. And sometimes it works better than or faster than your commercial software. Okay. So with this background, let me start with the topic. So the first topic, as I said, the first thing that we need to do is we need to prepare the data for predictive modeling, which we call it as exploratory data analysis. And what is exploratory data analysis? That we'll see in the next few slides. And then after that, this type is common for all the models that we'll be using. Whether you use linear regression or logistic regression, ARIMA, or extant, dysentery, neural networks, whatever you use, this type is common. So let's look at what is predictive modeling. What is EDA, or exploratory data analysis? So when we work with the data, we first need to understand the data that we are working on. This is called exploratory data analysis. So we try to get an intuition of the data, as well as we look at the semantics and check whether the data is correct or not. So that is EDA. Trying to understand data. Initial analysis to understand what it represents, and then we may need to transform data from one form to another form. And when we do that, that is called as data wrangling or munching. So if you work in this area, then you'll see this word wrangling or munching. It basically means you are changing the data from one form to the other. So that's called data wrangling or munching. So it more or less is the same thing. It helps. So if you are working with some modeling technique, And then if your data is not correct, then even if you use the most powerful modeling technique, your results will not be, your performance will not be good. Okay, so this is a very, very important step when we are working with predictive modeling or machine learning algorithms.
So one moment, sorry to disturb. The
Sure.
attendance form is not accepting any responses in the chat. We are telling. So if we request you, if you could.
Okay, so need not worry. So after this, I will again enable it. Okay, I'll enable.
Right.
Please check attendance.
Yeah, so after this session, let me complete this session. After this, I will circulate it.
Right, because it says that after 10:30 it will not allow.
Okay, I'll don't worry. I'll take care of it.
Yes, sir. Yes.
Yeah, please. Okay.
Thank you, sir.
I was talking about EDA, right? So EDA means you try to get an intuition of the data, and then after you get an intuition of data, you check the semantics, and if they're necessary, then you take the corrective steps. So why do we need EDA? So bad formatting. Bad formatting. For example, bad formatting. So, like for example, I was working once with this data, telephone data, and then so if you look at telephone data, some data will say it starts with +95, okay, and some you just get a telephone number. So now you need to change the formatting. You either put plus 98 or 95 to all the data, or you don't put this prefix to all the telephone data. So that's example of bad formatting. Trailing spaces. You may have duplicates. You can have empty records or missing values, and you can have synonyms or abbreviations. So this is very common when you are working with your social network data. You'll have a lot of abbreviations, LOL and all those stuff. But the machine doesn't know. So either you expand them or you use a standard abbreviation. And difference in scales. If the different features, they have different scales, then some of those features which have higher scale, they will weigh more on the bypass. Yeah, I requesting all of you to please mute your this one. And then we can also have outliers. So some of these we can deal directly when we are using some tool. Okay. So if we look at data, they can basically be of two types. One is categorical and the other one is numerical. Categorical basically means that this data is of string type. Okay, this is a string. So like name, okay. And this is numerical, number. And if you look at categorical, then they can again be nominal or ordinal. So nominal means the name of a person, gender, these are all comes under nominal. And ordinal means there's some ordering, okay, like grades, ranking. So now if you know that it is ordinal, there's some order, okay, then you can check the particular column and see that whether all the values are in that particular order or not. So we first need to find out whether it is categorical or numerical, and then if it is categorical, if there's some ordering in the data, if there's some ranking in the data. Okay. Again, numerical data, it can be discrete or continuous. Discrete means countably finite. Continuous means examples of continuous are speed, weight, temperature, and so on. So here's an example that we have used it in location privacy in one of our work. And then, so this is the kind of data that we get. So the first field is date. So date, it's numerical. So we check the date field and see whether all the data are in format or not. So we know that this is numerical. And in some places they call it, it can be discrete or it can be continuous. Time is again numerical. Okay. State is categorical, and it's nominal. So if you look at the state, then you will see that, yes, so there's an error out here. So just by looking at the data, you know that there's some error out here. Address, okay. There's missing values out here. There's some missing values out here. So this is EDA for you. You just look at the data, try to understand what the data represents, okay, and then you look if there are any errors. So I know this is a date field. I don't need to understand what this data is about. I know this is a date field. So all this particular column should contain dates. This is a state. So this will look at this will have valid names of states. So this is EDA. Okay. So once we understand, then we do the pre-processing. Then once we understand the data, then we try to take corrective measures. So for example, here there are missing values. So how to take care of these missing values? So the possible cleaning tasks are the days valid? These are the questions that we can ask. Do the nominal data have character variables? Nominal data, they should be of string type. So whether they have character variables. If they are ordinal, then whether they are in order. Okay, are the ordinal values within range? Are there missing values? Are there duplicate values? So these are the questions that we'll ask when you are doing the cleanup task. And there are some tools which are available. There are some tools which are available. So like, for example, we have OpenRefine from Google and data wrangling. So these are tools. With these tools, we can do some of the tasks like removing duplicate values, trailing white spaces, taking care of formats, and so on. But there are some things that which we need to do, which needs our intervention. Okay. How to deal with missing values. So if some value is missing, then how to deal with this? So one is like, you can just delete the record. So I don't need it. So that's the most easiest way of doing things. Okay. But the problem is if you delete a record, that record may itself be very informative. Okay. So if you once by deleting it means you are losing information. Okay. The other thing is if you are deleting the record and if you don't have enough data, then you'll not have enough data for meaningful analysis. So deleting the record you can do if you have lots of data, but you'll always run into the risk of deleting some information, some record which may be informative. So we need to impute, means we need to estimate a value for this missing. How to estimate? One is you fill the value with 0, but this is not good. So it's good as deleting the record. So it's not a good approach. The other approach is you take an average of all the other values in that particular column, okay, and fill the value with the average. So this may be a good estimate. Or you can also look at interpolation. Means you suppose on a particular day, the sales record is not empty. Okay. On a particular sale, on a Monday, the sales record is empty. So you look at the past week's sales record, Monday. Okay. And then you try to interpolate and say, you try to fill up this Monday's value with the last Monday's value. So this interpolation with similar data, you try to fill up or estimate with similar data. And then you will also check that Monday is not a holiday. If it's a holiday, then the sales record will not be good. So this dealing with missing values. Outliers is an observation which is far away from the normal values. Okay. So in this example, these two data points, they look like outliers. Okay. So I say, what is far away? How do you quantify this? How do you say an observation is far away? So there are some thumb rules. So the thumb rule says that if the particular data point is 3 standard deviations away from the mean, okay, then you can classify it as an outlier. So in the next session, we'll be dealing in detail with this EDA. In this next session means first session, day 1, session 2, we'll be dealing with detail of how to pre-process the data and how to visualize them using R language. So that's about pre-processing, the first part. So if you have any questions here, then I can take some questions, or else I'll go to the next section. Next section. Any questions?
No, sir.
Okay, thank you. Okay, so we'll look at the different ways in which we can do analysis. One is predictive or forecast models. So here we look at the behavior of a single unit in a data set. It is a single unit in a data set. For example, when you are trying to give a loan, then you try to predict the credit risk of the customer, whether the customer will default on the loan. The other one is descriptive models. Here we look into the data as a whole. So, for example, you look at the sales figure, okay, and then you're looking at the sales figure in the last 3 quarters, you try to predict what will be the sale for the next quarter. And accordingly, you try to put up your stock, okay. So that's descriptive model. And decision model means type of predictions are based on decisions, means you try to recommending rules to users, okay. The results of a decision, it comes under decision model. So in this particular talk, I'll be using this running example. Where I'm trying to predict a value of a plot. I'm trying to predict a plot, okay, based on the plot size and the locality. So this is a toy example which I'll be using to explain the models that I'll be looking at. So this column is the price of the plot, and this is the plot size, and this is the locality. So this becomes my dependent variable because this is what I'm trying to predict. And the plot size and the locality, these are my independent variables. So look at the dependent variable. The dependent variable can be of 3 types. It can be continuous. It can take on values from minus infinity to plus infinity. For example, plot price. So depending on the dependent variable, you'll choose your model. It can be binary. Means we want to know whether a particular customer will, when he makes an appointment, whether he will the appointment or not. So will they buy the plot? So yes, no decision. This is kind of binary. And the third one, the variable can take is qualitative. Means it's whether the plot is small, big, medium. Okay. So it's a qualitative decision, and this is a problem of classification. And when we are predicting continuous variables, then the tools that we can use for predictive modeling is linear regression, which we'll be looking in detail. And if the particular data has also temporal data, is time dependent data, then we can use time series. And this decision tree and neural network, these are very generic framework which we can use for all the type of variables, whether it's continuous, binary, or qualitative. We can use this model. So let's look at linear regression. So what is linear regression? So suppose say I have that example of plot price and plot size. Okay, I then make a scatter plot. Okay, then here what I want to do is there is a strong correlation between price and plot size. So as the plot size increases, the price also increases. So there's a strong correlation between the two. And then in linear regression, what I want to do is I want to find a line which best fits this data. So we can have multiple lines, and then I want to know which line is the best that fits this particular data. So that's why the name linear regression. We have a straight line, and which we try to fit to the data. And the linear regression model looks like this. So the linear regression model, you'll be again learning in detail in this next session, the coming sessions. But what we have here is we have the training set. We have the training set which is from M samples, and then this is the function that we want to build. Okay, this is the function that we want to build. This is the unknown function, and so this we call it as the hypothesis. And basically here we have this parameter theta transpose. So if it is a two variable, then theta, it can be like theta 0 plus theta 1 x and so on. Okay, so it's a straight line. And so this is the function that we want to build, which will predict the plot price depending on the plot size. So this may be the plot size, and this is the estimate that we want to make, the plot price. So in some cases you can also see that there's a white cap out here. It means we are trying to estimate the plot price depending on the plot size. And what is the cost function? The cost function is we want to minimize our prediction, and we want to keep our prediction as close as to the actual value for the training samples. So you want to minimize the cost. So this is there you can use different cost functions. So this is the squared error value. The errors, take the square, and then you try to minimize the square. So basically what we want to do, we want to learn this theta. We want to learn this theta. So we want to find those theta, those parameters, learning parameters, which will minimize this cost function for this particular hypothesis. So the way we do it is like we initialize theta to some random values, maybe 0, and then you keep on changing theta to reduce the cost function. You keep on changing theta at each iteration to reduce the cost function. And this approach is known as gradient descent. This approach is known as gradient descent. So basically, if you have something like this, so you start from a point out here, and then you keep on going down, and each iteration you take some small steps, and then you finally reach the bottom. So you look around and you choose that particular value which is the minimum. So this gradient descent is kind of looks like kind of a greedy approach. Okay. From among the values that, so if I'm standing out here, then I'll choose the value which is the minimum, which minimizes which is the minimum cost function. Okay. And then I'll take the step there. Then again I'll take next step and so on. So it's like a greedy approach, but why it works out here? Because our cost function is a convex cost function. So it has only one global minima. So it will always converge here. Okay. And then what we need to do is when we are doing this, we need to understand what is this alpha. Alpha is learning rate. Alpha is learning rate means the steps that we take. What is the step? The step size. If you take one step size, then we may miss the global minima. If you take very small step size, then it will take a long time to converge. So when we are working with linear regression model, this is one parameter that we need to set, the learning rate. So this is a very simple model.
Hello, sir.
Yes.
Sir, in the previous slide,
This
yes,
one?
this one. Yes, sir. Sir, what the theta basically represents, x is basically the independent variable, then h and the suffix
Theta are the weights. Theta are the weights. Okay, like based on theta, I'll this straight line will depend based on data theta. So ax plus b. Okay, so what is a? What is that? These are my theta. So this straight line will depend on this a and b, right? How this straight line? What is the straight line?
Sir, A is the intercept term and B is the gradient actually.
Yeah, b is the gradient. Okay, so depending on these, my straight line will depend. So basically, I want to learn this. Okay, but I may have a lot of this. So you'll see the next slide that I may not have only one variable, dependent variable. I may have a lot of independent variables. It will become more and more complex. That's why I've written here theta transpose. So this is what I have in the next slide. Okay. So you may not have only the 1 and 0. So it will not touch like this, it will go on like this out here, means at 1. So when theta transpose x is very large, it will asymptote at 1, and when it's very small, then it will asymptote at 0. And the cos function here is this. So if yi is positive, then only the first part will contribute to the cos function, and if yi is 0, then only the second part of the cos function will contribute to this cos function. And again, for learning this parameter theta, we'll again be using the same gradient descent function. Okay. Only thing here is the hypothesis is different. Otherwise, the approach to learn this theta parameter is the same, the gradient descent.
Hello.
Yes.
Sir, in case of logistic regression, the value of the dependent variable will be ranging from 0 or 1. It will be either 0 or 1.
In case of?
The dependent variable, the value of y will be either 0 or 1.
In case of logistic?
Yes, sir, logistic regression.
Yes, yes, yes.
Sir, if it is 0 and if it is 1, then should it be an asymptote? Because if it is 1, then it should be touching 1, or
yeah, means what I'm saying is, so if you draw the plot for this yi, the plot will be something like this. If you draw the plot for yi, it will be like this. Okay. So means the cos function. So this is this side cos function, and this is your theta transpose x, the hypothesis. So what I mean to say is that, so suppose your value, this is your yi is 1. Okay, if your yi is 1, then so it will predict a value which is close to 1, so means your cos function is almost 0. Your cos function is almost 0. And if your yi is 1, okay, if your yi is 1 and you are predicting that is 0, then your cos function will be very high. Then your cos function will be very high. So the curve for, because in this I said only the one part will contribute in the cos function. So the cos function for yi will look like this, and the cos function for yi equal to 0, y equal to 0 will be just the reverse of this. So if the value is yi is 0 and you are predicting 0, means the cos function will be close to 0, very close to 0. Okay. And if the actual value of yi is 0 and you are predicting 1, means the cos function will be very large out.
okay, sir.
Okay. So this is how the cos function will look like individually.
Sir, this is a plot of a cost function or S theta?
Yeah, S theta versus cost function. Cost. S theta versus cost. And this is how the sigma, this is, and this particular plot is a plot of the cost function, your S theta. This is 0 out here, this is 1 out here. Okay, so we'll go to the next model, that is time series. So in time series, there is a...
Excuse me, sir.
Yes.
Sorry for interrupting, but I just had a small question
Yes,
of the previous slide. it could be a very naive question, but as you said, sir, that it could only take the value between 0 and 1. So looking at the graph, does it also suggest that it can take any value between 0 and 1, including 0 and 1?
Yeah, so yeah, I'm not giving you details. So if it is so for example, there will be a probability. There will be a probability function which says if your hypothesis is greater than 0.5, then you predict it as 1. Yeah, you are right that you can take values between anything between 0 and 1. Okay, it can take some value out here. So
Okay.
if some value out here, then I'll predict it as 1. If it takes some value out here, then I'll predict it as 0.
Okay, because otherwise I was thinking it takes any value between 0 and 1, so it becomes
yes,
a
you are right.
continuous function, right, sir?
Yes, you are right. You are right.
All right. Okay, thank you, sir.
Yeah. So in this next thing, we'll look at time series. So time series, there will be 2 sessions on time series. One will be an ARIMA, autoregressive model, and then one will be an error trend. But what I'm trying to do in this particular session is, I'll just try to introduce what are some of the things that you should look into when you are looking at a time series model. What are some of the terms that you should know? Okay. So this is a formal definition of a time series. So here you see this is my dependent variable again. Okay. But now the independent variable, we don't have X, but we have the lag values. We have the lag values, means these are my previous observations of the same variable. Okay. So at yt, this is the variable, this is the value, and at yt minus 1, t minus 2, what are the variables, what are the values of this particular variable y that's given out. So a time series is an observation measured over a period of time. Now, when we look at time series, there are 4 things that we should know. You may not know in detail how it works, okay, but these are the 4 things that you should at least know. But you need to worry. We'll go into detail. We have experts in time series who will be giving all the details. But as a user, you should know these 4 things: trend, seasonal, cyclic, and irregular. So if I look at a time series, okay, the tendency of a time series to increase, decrease, or stagnate over a period of time, that is called as trend. So in this particular example, this time series, it has a tendency to increase. But this trend is only for for a particular interval, and it does not repeat. It does not repeat. So there's the keyword out here. It does not repeat. So there's a trend. Like for example, when a new song is released, like for example, now this new song has come, no? When it has become viral from Sri Lanka. So you see the trend, so it will have a very steep slope, but this will not continue forever. Okay, after some time it will fall down, and then this trend will not repeat. So this is trend, means the tendency to increase, the number of people who are listening to this particular music, they keep on increasing, okay, but it does not repeat over again and again. That's trend. Seasonal means the pattern, okay, the pattern keeps on repeating depending on the season, okay. Season here can mean year, it can mean the week, and so on. So when you're working on this computer center data, so if you look at computer center, so in our institute, computer center is the place where all the network and the internet is controlled by the computer center. And then we keep on monitoring the data, and I was working at computer center before. So we observe is that during the daytime, so if you look at the day, if during the daytime the data will be like this because all the students are attending class, and then as soon as the evening, then it will peak because the students are now in the hostel. They'll start using the internet. It will peak, and then it will go on throughout the night. Maybe they sleep very late, and then it will again, when day comes, then again fall down, and again the same thing will repeat. So this is seasonal. Okay. the pattern occurs repeatedly depending on the time of the day of the week, or month of the year. And then cyclic, again, it's repeats, but here the frequency is not fixed. Cyclic. And random or irregular, it means there's no pattern. You cannot associate any pattern with it. Okay. So unpredictable influences happens during epidemic, flood, war, etc. So there's no pattern involved in the data. And then one other term that we should know when we are working with time series is autocorrelation. So what is correlation? So you can, from this word itself, you can understand what it means. Correlation means measure the relationship between two variables. And when you say auto, means it measures the relationship with itself. Okay, so it measures the relationship between the lag values of a time series. So when the data have trend, okay, the autocorrelations tend to be large and positive. And when the data is seasonal, the autocorrelations will be large. And so why do we need to know these terms? Because forecasting time series is difficult as it is non-deterministic in nature. Okay. So when we are forecasting a time series, then it must be stationary. The time series must be stationary. And what do I mean by stationary? The stationary means statistical properties such as mean, variance, autocorrelation be constant over a period of time. And if your data has any of those properties which are just shown, like if it is trend, if it is seasonal, okay, if cyclic, okay, then it will not be stationary. Then you need to do those things. So there are statistical forecasting methods are based on the assumption that the time series can be rendered as approximately stationary after some mathematical transformations. So if your data is not stationary, then you need to make it stationary by using some transformation. So you first need to check whether there is those trend, seasonal, all those things are there in the data or not. And if it is there, then you need to remove them. So these are the two models that we'll be looking at. One is your auto-regression model or auto-regressive integrated moving average. So here, basically, when you are looking at ARIMA, then you need three parameters: P, Q, and D. And we'll be looking at these parameters in detail when we do this session. So means auto regression, it has two parts. One is the auto regression part and the other one is the moving average part. So this P parameter is associated with auto regression. How much past values you look at? What is the moving average window? That is Q. Okay. And if the data is stationary, then you need to differentiate. So this is the differentiation parameter. The other model that we will look at is ETS, error transitional, and these are two popular models for time series forecasting. And the difference between these two is, in case of ARIMA, it works only for stationary time series. So if it is not stationary, then you need to make it stationary. And ETS model, it can work for non-stationary model also, without converting it. So this particular models we'll be looking at on day 2, session 2, and day 3, session 3. ETS will be looking at in day 2, session 2, and ARIMA will be looking in more detail in day 3, session 1. And decision trees will be not looking in detail. Decision trees means we don't have, but I just gave it because it's also one of the most popular models. So what we do is we divide the search space. We divide the search space into disjoint set of rectangles and feed a simple model. So what I mean to say is, suppose you have a, I think I've got an example out here. I've got an example out here. Okay. Let me go to the example directly. So, like for example, in this decision tree model, so this interval here, it says that what is the interval between the appointment time and whether the appointment date. Coming to that example of customer approaching the seller to buy a plot. So it says that if the interval is less than 7, then the customer keeps the appointment. If the interval is greater than 7, okay, the customer may keep the appointment or may not keep the appointment. So then it will depend on his income. So if his income is less than 25 lakhs, then maybe he'll not keep the appointment. And if it's more than 25 lakhs, then he'll keep the appointment. Or then we can also have more features out here. So what we'll do is, so if you look at this particular decision tree, okay, so suppose this is my search space. I want to know whether we'll keep this appointment or not. So interval less than 7. So if this interval is less than 7, so let's say this is this one. So interval less than 7. So then I'll look into only this and then they keep the appointment. If interval is not less than 7, then they may not keep the appointment. Then I need to look at the income. So then I look at this part of the search page, and then income. So this is my line for income. This is my line for income, for example. So income less than 20 is cancelled. Income more than 25, it keeps the appointment. So this is how we divide the search space into rectangles using the features. So this feature is the interval feature, and this feature is the income feature. So that's what I've written out here. We divided feature space into this set of rectangles and fit a simple model in each of these rectangles. So those who have worked on binary search tree, you'll know that this binary is something that looks like similar to binary search tree. The only difference here is the same feature can occur more than once in the model. The same feature can occur more than once in the model. And then the leaf nodes have the specific outcome. So finally we'll reach the leaf node, and the leaf node will tell whether the customer will keep the appointment or whether the customer will not keep the appointment. So tree models are very versatile. They can be used both for regression and for classification. And they can have both continuous and categorical predictors. Okay. Only the shortcut is if the class boundary is not horizontal or vertical. So if the class boundary here is not horizontal or vertical, means if the class boundary is something like this, then it may not work. So this is tree model for you. And then finally, we'll look at the last model in this particular session, that is neural networks. So before I started neural networks, let me tell you what are the steps in machine learning. So we have seen, so just to review what we've done. So when we do any kind of machine learning, we first have the input data, that is called a training data, okay, and that is of m samples. And what we do is we choose a function to feed our data. So that is called as a decision function or the hypothesis. So here I have written it in a different way. So I want to estimate the dependent variable. And this is my unknown function, which I want to build. So for linear regression, it will be a linear function. For logistic regression, it will be a logistic function. Okay. And for neural networks, it will be a different kind of decision function. So the different training models, different machine learning models basically depend on how you build this particular decision function hypothesis. And then based on this decision function, we'll have a cost function which we'll try to minimize. Okay. So in case of linear regression, we looked at this mean square error. And then what we do is, after that, once we have built a model, then we try to learn the parameters. We try to learn the parameters, that is the theta. And when we are learning these parameters, then what we do is, when we have learned the parameter theta 0, theta 1, then we learn these parameters and then we apply these parameters simultaneously to the cost function. We don't learn the first parameter and apply to the cost function. So this learning is done and the parameters are applied simultaneously to the cost function. And for gradient descent, we need to know the learning rate, alpha. This is important. So if I look at linear regression, then this is my input. Okay, this is my input. Just to review what we have done, this is my input. And then we learn these weight parameters, theta 1, theta 2. Okay. And then we have our output out here. So there are two layers out here, the input and the output. Similarly, if you look at logistic regression, again we have two, this one, layers, the input layer, we have the input layer and the output layer. We have the output layer. The only thing is, here the hypothesis is different and the cost function is different. Now, when we look at neural networks, so there is a third layer which is present. There is a third layer which is present, which we call it as the hidden layer. So there's the input layer, there is the output layer, and there is the hidden layer. Why do we call it as hidden layer? Because this layer is hidden, so only the input and output is visible to other systems. Okay, and the hidden layer is only visible in the neural network and it's not visible outside. So that's why we call it as hidden layer. And in a simple case, this hidden layer, we may use the same function as the logistic function. So if you look at each of this hidden layer, okay, what we do is a weighted sum of the input, okay, and we apply some activation function. So if you look at this figure, you see what is this? It's nothing but the weighted sum of the inputs, and then you so at each hidden node, what we do is we have a weighted sum of the inputs, and then we execute an activation function. So in the simplest case, we may use that logistic regression function. And then finally, we'll have the output. So neural network, again, we'll be learning in detail on day 3, session 2, and day 4, session 1. This is the model for neural network. We again have the input. So in the simplest case, I said we can use the hypothesis of logistic function, logistic regression. And this is the cost function here. So this extra term out here, k equal to 1 to k. So this is for the layers, number of layers. And then for parameter learning, we here use forward propagation and to compute activation of each layer and back propagation. So this will be learning in more detail on this particular session. Now the question is, why don't we, so this neural network works for all the model. Means it works for all the cases. It will work for your continuous variable, it will work for binary variable, work for time series. Then why don't we use neural network everywhere? So the problem with neural network is it is compute intensive. The first the issue is it's compute intensive. So if you look at its history, neural network, so it has been around for quite some time now. It has been around for quite some time, but in between it was not very popular because it was very compute intensive. But nowadays, as computers have become more and more powerful, this neural network model has become very popular nowadays. Okay. The other reason why we cannot use neural network everywhere is it requires a very large training sample. If it requires a very large training sample, so if you have small training samples, then you will not be able to use neural net. So the design issues here are what will be the number of hidden layers that you will want, this depth. So for most cases, we'll be using only one hidden layer. That will be one hidden layer will be enough for most of your problems. Okay. Then the number of units per layer, the number of nodes per layer, the width, the time of the activation function, and the form of the cost function. So these are the basic design issues that you need to look into when you are working with neural networks. So for regression, you can use the same, for regression, you can use the same objective-based linear regression, and for classification, you can use same objective-based logistic regression. Okay, so I'm at the end of my slide. If you have any questions, I can take some questions. Now. We have around 10 minutes in this session.
It will be better if you will post this PPT also, sir. We get this PPT.
Yeah, I'll do that. Maybe I'll post all the PPTs. We'll see if I can post this PPT today itself. Okay, and then I'll post all the PPTs.
So we can have one Google Classroom or somewhere, right? So that you can have all the notes together.
Okay. Any more suggestions? Any more questions if you have? So what I've done basically in this lecture is I've just outlined the steps that you going through in this particular course. Okay. So EDA will have, just after this session, we'll be looking in more detail. Okay. Explorative data analysis, pre-processing, and you'll be using R. And then how to predict continuous variables. We'll be using linear regression for that. It's a simple approach. And you can use this approach if you don't have much of training sample. And you can use this as a baseline approach. And if you have a binary variable, binary outcome, then you can use logistic regression. And if you have time series, then you can use ARIMA or ETS. And then in my last session, I'll be using ARIMA for one of my case studies. I'll be using ARIMA, and then I'll be using SVR. So I'll also deal with SVR on the last day. And then machine learning models will be looking at neural networks in detail in the coming days. So that's it for me from now. If you have any more doubts, then we can take the doubts, or else we can end the session.
Sir, I have one more questions. In ARIMA, right, you said that we are making the series stationary. So if you will make the series stationary, then how will you be able to predict the trend or any other pattern in the data?
Stationary in the sense we'll be using differencing. We'll subtract the previous, so that if there's some trend available, then the ARIMA model will not work properly.
So it is just used to predict the data which is of varying around the constant, right? Is having some label data.
Yeah. So yes, means you may think that the data is constant. So the prediction will be, but what we'll do is we actually may have data, but in practice, what we'll do is we'll see that data is not stationary. Most of the practical data will not be stationary. They'll either be, they'll have trend or they'll be seasonal. So basically we'll be using some methods to make it stationary, but we are not removing the actual data out of it.
But so we also have S ARIMA, like for if we have to consider the seasonality, we have as S ARIMA.
Yes, we have as you can go for ETS. You can go for ETS. So I'm looking at some of the basic models. You can go for ETS where you don't need to remove the seasonality. So we'll be looking at both kinds of models where you need to remove the make it stationary, or without stationary, making it stationary also you can work on the data. Yes, any more questions? Okay, then we'll stop this one. The next session will start at 11:30. So I'll share this one. I'll share this, and I'll share the attendance link also with you. I'll just talk to my technical team and see why it's not being done. Okay. So this meeting will continue. This meeting link will continue, and then I'm new to this, so.
Hello.
Yes.
So can you share the recording session?
Yes, I'll do that. Yeah, I'll do that. We are recording it, so I'll share a recording session with you.
Yeah.
And I'll share the meeting link. There's attendance link also with you. So right now, so we'll take a break now, and then we'll start the next session from. Next session is from 11:30, I suppose, right? Yeah, the next session is from 11:30. So we'll have a.
Sir, once to open the attendance link, sir, we are in the class, but now it is disabled.
Okay, just give me a minute. Just give me a minute.
Okay, sir.
So please share the link again also.
The attendance link.
Yeah, sir, please.
Yes, I'll do that. Yeah.
Please share the attendance link, sir. Good morning.
Sure. I'll do that. Yeah.